Hi guys, just want to run you through these notes on z-scores so you have it. So we talked about it today in class, but z-scores, essentially a z-score is the number of standard deviations away from the mean. And it standardizes any data values to be on the standard normal distribution with a mean of 0 and a standard deviation of 1. So the formula for it really is quite simple. We have two different ones here, one for a population, and remember, when you see the Greek letters, it's talking about a population. So x minus mu, we're going to take any individual data value x, and we're going to convert it to a standardized z-score. In other words, how many standard deviations from the mean is x? So if you subtract the mean, and then divide by the standard deviations, that would be, divide by the standard deviation, that would be the number of standard deviations. And for a sample, we just use x bar to represent the mean of a sample, and we use s to represent the standard deviation instead of sigma. Let's run through an example here. Example 1. So you may or may not have known this, but when they design SAT questions, when they design the whole test, they build it such that it's going to be normally distributed for all students taking it with a mean of 500 and a standard deviation of 100. Now, they don't hit that perfectly usually, but that's the goal of the test, and they make adjustments yearly to make that happen. So let's assume that we do have a mean of 500 and a standard deviation of 100, and someone scores a 320 and someone scores a 730. Well, obviously the 320 is below the mean, not quite 2 standard deviations, because 500 minus 200 is 300. And the 730 is a bit more than 2 standard deviations above the mean, so the 320 is going to have a negative z-score that's almost 2, and the 730 is going to have a positive z-score that's a bit more than 2. And you can see in the formulas there, we are using the formula for population, since we are given the population mean and standard deviation. So we're using mu and sigma. Remember that you always subtract the mean from the data value, even if the data value is less than the mean. So in the first example of 320, you will get a negative number on the top, negative 180, and you divide that by the standard deviation. And think about that. That is going to tell you how many standard deviations does it take to get 180, which is the number of standard deviations. So negative 1.80 would be the z-score for an SAT score of 320, given those parameters. And for the 730, same process. That's 230 points above the mean with a standard deviation of 100. That means you're 2.30 standard deviations above the mean, and that's what a z-score is. Okay, and it does have a note here that z-scores are normally reported in hundredths. So round up to the second place after the decimal. Another example. In a recent study in India, a sample of adolescents had a mean screen time of 3.8 hours per day. It doesn't tell us how large the sample is, but that's irrelevant in this calculation. Hopefully it's representative of the population. We know that's important. And a standard deviation of 2.77 hours per day. Well, right away that tells me that the standard deviation is large compared to the mean. So there is a lot of variation in this sample. But again, all we're doing is calculating a z-score here. We're not thinking about that stuff yet. So let's go ahead and calculate a z-score. This time we are using the formula for a sample. X bar represents the mean of the sample, S represents the standard deviation of the sample. Okay, and it's asking about a one singular adolescent student. Actually, it doesn't say student. One singular adolescent who had 7 hours of screen time. Well, obviously that is well above the mean. But with such a high standard deviation, it's not that many standard deviations above the mean. So this data is really spread out. If we looked at this distribution, it would be not a very high peak to our normal curve. And we'd have the mean here of 3.8, but with such a large standard deviation, we'd be way out here. And this particular person is about right here. Okay, so 7 minus 3.8 would be the number of hours above the mean that this adolescent is. Divide that by the standard deviation of 2.77 for a z-score of 1.16, or 1.16 standard deviations above the mean. We talked about this a little bit in class. The range of reasonable values for any normal distribution is within 2 standard deviations of the mean. So if you think about the normal curve, go 2 standard deviations above, 2 standard deviations below. Anything within that range is reasonable. Anything outside that range is considered unusual. Okay, so here talks about in the above examples, an SAT score of 730 is unusual. Recall that it was more than 2 standard deviations above the mean. It was 2.3 standard deviations above the mean. So that would be considered unusual. And yeah, if somebody scored a 730 on one section of the SAT, I guess that is, math or English or writing, that would be really good. An SAT score of 320 is well below the mean, but it is not considered unusual. It wasn't 2 standard deviations below the mean. It was only 1.8, so not quite in the unusual range. Okay, the 1.16 for the screen time is not unusual. Okay, and then there's a note here that the unusual label is related to the population or sample that the individual score belongs to. The math score of 730 is referring to the entire population of people taking the SAT, but if you change your population to students admitted to MIT, then that would certainly change the mean and the standard deviation, and you would most likely find that a score of 730 on the math section was not very far from the mean, not many standard deviations from the mean. In fact, it might be below the mean. So it does depend on your population or your sample. All right, I'm going to let you do the guided practice on your own, and I will make another video where I go over these problems, and we'll see you then. Hope this helped.